Hi, I'm Matthias Beck. I'm one of the authors of Computing the Continuous Discretely. And in this video, we will start our discussion of zonotopes. And these are the content of Chapter 9. A zonotope is the Minkowski sum of line segments. So I should first tell you what a Minkowski sum is. Here's a definition. You have a bunch of polyhedra, let's say n polyhedra, P1 through Pn, and their Minkowski sum is defined as pointwise addition. So I think of my polyhedra as all living in the same space R to the d, and now I'm defining their sum to be all possible sums of points xi living in pi. On the left you can see an example where I have three polytopes that are line segments, and their pointwise sum, their Minkowski sum, forms a hexagon. And that gets us to the definition of a zonotope, and that is it's the Minkowski sum of line segments. If my line segments are formed by linearly independent vectors, then the zonotope that's generated by them is a parallelepiped. And so one way of thinking about a zonotope is as of a concept that generalizes the notion of a parallelepiped. On the top right, you can see an example of a zonotope in 3 dimensions. And here you can see a formal definition. So today, when we use the notation Z of U1 through UN, so U1 through UN are vectors that live in some d-dimensional space, then here's a definition of the zonotope generated by those vectors. And just so we're clear about the definition, I will always allow a translation. Let's play a little bit with this definition. So in the second line here, you see again the definition of a zonotope as the Minkowski sum of line segments. But in the third and fourth line, you can see that we can rephrase this definition as coming from an image of the n-dimensional unit cube. So here n is the number of line segments that I start out with. And this matrix A is the matrix whose column vectors are the initial vectors U1 through UN. So this gives you an alternative definition. A zonotope is also a projection of some unit cube. And by sum here, I mean you get to tell me the dimension. And then again, I can translate the resulting polytope. I hope you can see from the pictures on this page that zonotopes are quite beautiful objects. They can be quite intricate, and they have lots of connections to various concepts in combinatorics and geometry. What we'll do next is a natural decomposition of zonotopes. For general polytopes, we have learned that a natural decomposition is by simplices. This is what we call a triangulation. Turns out for zonotopes, the natural way to decompose is via parallelepipeds. Let me start with an example. So this is the hexagon from the previous page. What I'll do now is I will take a set of linearly independent vectors, like maybe these two, and complete them to a parallelepiped. And I will do this with the next set, maybe these two down here. And then you can see in the last parallelepiped that I need up here is formed by the, if you want, the first and the third generator of the Zonotope. I claim there's nothing special about what I'm doing here. This works in any dimension for any number of generators. And this is actually something you can think about relatively easily. So if you want to grab a cup of coffee, you're welcome to pause the video for a moment and think why this holds in general. But it turns out there's an even better decomposition that I can do using half-open parallelepipeds. What I'll do now is I'll start maybe with the origin, and I think of this as a zero-dimensional parallelepiped. And then I take one of my line segments, maybe this one here, and make this sort of half-open where I'm not including the origin. I can do this the same for this second line segment over here. And now I can complete my first parallelogram here using a half-open two-dimensional parallelogram. And you can see I can keep going with this. So here's another half-open line segment, another half-open parallelogram over here. And then I need another half-open parallelogram up on top here. So philosophically, what's going on here? I considered all possible linearly independent subsets of my original three vectors. So this could be a subset with no vector, one vector, or two vectors. I formed a half-open parallelepiped of the correct dimension for each such subset. And then by possibly translating the resulting parallelepipeds, I get a disjoint decomposition of my given Zonotope. And what I've done here is always possible. This is stated in lemma 9.1. So I can take a given Zonotope and write it as the disjoint union of certain translates of half-open parallelepipeds. Those parallelepipeds are generated by linearly independent subsets of the given vectors, and I need exactly one parallelepiped per subset. The notation is a little bit hard to parse. These sigma sub j up on top are simply signs, and those signs tell you, if you want, in which way my parallelepiped is half-open. It's not entirely trivial to prove this lemma. In some sense, it should remind you of what we did with triangulations. The way we initially approached triangulations was through regular triangulation, and there's a notion of a regular tiling of a Zonotope, and you might think about how you want to do that. Another way to prove this lemma, and this is what we do in the book, is an inductive proof on n. In this simple example, the induction step looks something like this. You have a given tiling, let's say the orange tiling that you see in my picture, and then you construct additional parallelepipeds with your new generator that you have not used. So in induction step, I will produce a one-dimensional parallelepiped that sits on top of this zero-dimensional parallelepiped that's the origin. And then I will produce two two-dimensional parallelepipeds, parallelograms. One that sits on top of this half-open line segment here, and the other one that sits on top of this half-open line segment up on top. Of course, this is only an example, but it gives you an idea how to construct a proof of lemma 9.1 in detail, and you can read those details in section 9.2. These tilings of a zonotope into parallel pipettes have many consequences. The most immediate for us is based on the following kind of simple fact, and that is, if you give me a parallel pipette, and I think of it as a zonotope spanned by d vectors, let's say, and I make it half open like this, but this is arbitrary. I can switch the inequalities for each index. Then the number of integer points in pi, in this parallel pipette, is equal to the volume. And from your linear algebra class, I hope you remember the volume of a parallel pipette is given by the determinant of a square matrix formed by the generators. I have to take the absolute value of the determinant. Let me give you a picture at least why this is true. So if I think of my parallel pipette as, let's say, half open like this, then I can start dilating. Let's say I'll take the second dilate of this half open parallel pipette. And I can now tile actually using translates of my original parallel pipette. And so everything matches exactly because my parallel pipette is half open. And that means that actually not only the integer point count is equal to the volume, but you have sort of an Erhard polynomial, at least if your generators are integer vectors, which we assume right now. Your Erhard polynomial of this half-open parallel pipette just has one term. It's given by the volume times t to the correct power, which is the dimension. Anyway, if we now use this lemma in our tiling of a zonotope, we get the following corollary. We have a lattice zonotope, if our zonotope is generated by integer vectors, and then fix the tiling that you saw on the previous slide, then we can compute the coefficients of the Erhard polynomial of the zonotope using relative volumes of those parallel pipettes in the tiling. Remember, in our tiling, we had parallel pipettes of all dimensions. So for example, there's one zero-dimensional parallel pipette with relative volume 1, that will be the constant term. But what we're now saying is that all different dimensions of parallel pipettes give a contribution to the corresponding term in the Erhard polynomial. In the next video, we will refine this result and give a quite concrete formula for the Erhard polynomial of a lattice zonotope.